Hello physics students. In this video, you're going to learn how to apply Gauss's law to cylindrical symmetry. Now remember, in the distributed charge unit, we studied how to find the electric field for a charge bar, and the process was long and tedious. What we had to do is to find the electric field at the midpoint. We had to imagine slicing this up into little segments, dx length, charge dq, such that we could use the formula for the electric field of a proton or an electron at this point, kq over r squared. We found from the geometry the length of that dE arrow, and then we integrated over the whole bar, and we found a net expression for the electric field pointing away at the midpoint. And then we allowed the length of the bar to grow to an infinite length, and we found a formula for the electric field of an infinite line of charge. And that process took 4 boards, and the integral involved was very tedious and difficult. At the end of it, I promised that when we got to Gauss's law, we would be able to solve the same problem in 3 lines. So that's what we're going to begin with today, the infinite line of charge. So Gauss's law, cylindrical symmetry 1 for the infinite line of charge. Let me explain this first, and then I'll give you an opportunity to copy it down later with a pause. So infinite, again, is a relative term. We could call a wire that stretches from one side of the room infinite as long as the length of the wire is long compared to how far we are from the wire, much longer. And then the symbol we use for the charge density in a line, the coulombs per meter, is lambda out of the Greek alphabet. So that's how packed the charge is along a line, or how not packed, or how unconcentrated. So here's our line of charge. Here's Gauss's law. Now, you see, here's the solution. Nice and simple, 3 lines. But in order to use Gauss's law, you still need the distributed charge unit, at least the thoughts, to cue you in about what kind of Gaussian surface you're going to use. It's a cylinder, as I've drawn here. Now, how do we come to that conclusion? Now, remember, in spherical symmetry, we use the sphere. In cylindrical symmetry, we use the cylinder. So here's a diagram of an infinite line, infinite length of charge, okay? And so here's a Gaussian surface, a cross-section of a cylinder. And the reason why we use a cylinder is because we know from distributed charge that, first of all, if I pick a little dq here, it makes a dE here, as you can see, the red dq, the red arrow. If I pick another dq, the same distance to this side, it makes a dE like this with the same horizontal component as the original one. Those two add to produce a net electric field upward, a dE net. Whatever point I pick over here, there's another point symmetrically on the other side, canceling its horizontal component. So I know that dE is always going to be perpendicular to the surface of the cylinder. In other words, the dot product between dA and dE is just, the cosine is 0 degrees, so I have just dE times dA as a scalar instead of a vector. Furthermore, I know that because this line is infinite, everywhere along here, I'm going to have the same electric field pointing outward. And so then, what that does, those two facts, always perpendicular and the same magnitude electric field all along this surface, that then means that I can eliminate this dot product vectors, take the constant electric field out of the integral, and just integrate dA, which just becomes the surface area of the outer edge of the cylinder. So these ends have no flux through them because the electric field points radially away from the line of charge. So there's no flux on these 2 ends, only along this outside surface. So the area, dA integrated to area, we can find because that cylinder, when it opens up, becomes a rectangle. And the area of that rectangle is length times width, and that width is the circumference of that circle. So this is 2 pi r length times width, the area of the Gaussian surface. the charge enclosed inside our Gaussian surface is the coulombs trapped inside that cylinder. And I've tried to draw this in blue. Hopefully this shows up on the video. That's the portion where the charge is. And the coulombs in here will be the coulombs per meter times the meter of our Gaussian surface. So there's the coulombs inside. And then all I have to do is solve for electric field by dividing both sides by 2 pi r L. The L's, of course, cancel. So there's the electric field. 3 lines, nice and easy. As always, I recommend doing a unit check. Remember, the electric field always has units of the coulombs constant, then kq coulombs over r squared. And you can see here that I have the units of k because I have 1 over epsilon 0. So unit-wise, that's k. The lambda is in coulombs per meter. And then I divide by another meter, and I get k coulombs over meters squared. So the formula has the right form and the right constants also. So there it is, nice and simple. All right, now let me pause, give you a chance to copy this down. Okay, the next example, B, infinite coaxial cable. What is a coaxial cable? Well, now, of course, we have HDMI cables, but before HDMI cables, they used a coaxial cable for signals, like for television or whatnot. And basically, well, let me see, help the camera focus. A coaxial cable is one conductor inside. This is now a plastic insulator. And then this is another conductor. You see there's a foil, and then this wire mesh and another foil. So these all contacting make like one conductor, effectively one conductor. So what we have is one conductor, thin, inside of another conductor on the outside. And when you use this for communications, what happens is this outer conductor shields the inner one electrically from outside interference. So it was the first or an early way to have television, movie signals or whatever go through and be protected. Of course, now HDMI does it with different ways, or Ethernet cables. But what we're going to do is we have an infinite coaxial cable. So there's one thin conductor going through the center, and then a shell on the outside. And the inner conductor is charged up, but the shell has a charge of 0. So the lambda equals 0 for the shell. It's uncharged, okay? And what we want to do is find the electric field in all the regions. I didn't write that out, but basically that's what we're doing. So the first thing, for r less than r, in other words, in this gap over here, basically I'm not going to resolve it because we would just do the same thing as we did here. We just make a little Gaussian surface, a cylinder around this inner conductor, the left side, the right side, all the same, and we get the same formula. So go ahead, I'll pause and do your best to draw this diagram. I have fun with the 3D shapes, and then just write the answer because it's the same as the previous example. Okay, let's go on to the next region. Inside this conductor on the outside, okay, so the shell. In other words, for r greater than capital R, but less than 2r. Well, it turns out the answer is just 0 because we are inside of a metal right there. And we know that the electric field inside a conductor in static equilibrium is 0. Even though we've got charge here, it's shielded by the metal material in there. And then finally, for r greater than 2r, in other words, at a point out here, what I would do is make a Gaussian cylinder wrap around the whole cable. So like in real life, you know, here's our cable and we just have a Gaussian cylinder wrap around it, okay? So the derivation is exactly what I just erased. Because once again, the electric field is a constant over that cylinder, and it's perpendicular to the cylindrical surface, so this constant E can come out of the integral. We're just integrating dA around this cylinder. So E times 2 pi RL is the left side. The Q enclosed, once again, I have a certain lambda coulombs per meter times meters inside of my cylinder. The coulombs per meter times the meters is the coulombs inside. And then the L's go away, I divide, and I get the same formula again. By the way, the left side for cylindrical symmetry, it always just becomes E times 2 pi RL. Okay, so that's, in spheres, it was always E times 4 pi r squared, the surface area of a sphere. This is now the surface area of the cylinder. All right, as usual, we can be required to graph this. So jot that down, and then I'll put the graph up next. Okay, so the graph. So notice these formulas are the same because I'm going to erase this formula over here. And so the electric field formula would look something like this. So inside here we have a 1 over r graph. So from okay, and then the same formula out here. So this is proportional to 1 over r, and so is this. But in this region, in the metal, the electric field drops to 0. So E equals 0 here. We can also put the transition values here by plugging in capital R into this formula. So I'll put it all as one formula, lambda over 2 pi epsilon 0, capital R. And then this transition value right here, we can plug in 2r into this formula, the outer edge of this cylinder. And there is the graph. Okay. All right, so go ahead and jot that down. One final thing I want to do about the for the coaxial cylinder is sigma on the inner surface. So what am I talking about? Right here. If the electric field ends up being 0 over here, that means if I make a Gaussian cylinder that encloses the inner surface and this line of charge. In other words, it's a cylinder that goes like this and goes around and it has a certain length. If the electric field is going to be 0 in there, that means Q enclosed is 0. So we know that for that Gaussian cylinder that goes like this, right, from here to here, and it's a cylinder, then we could say that Q on the line equals Q on the inner surface of the shell. In other words, the lambda times the L, the coulombs per meter, will be the sigma times the area of the inner surface. And the area will be 2 pi RL, as we determined earlier, of the outer edge of a, that's the inner surface right here that the charge is on. And so I can eliminate the L. Well, maybe I won't do that because then it looks like a 4. but the L's go away, and I could solve for sigma on the inner surface, lambda over 2 pi r. Okay? And you can do the same thing for the sigma on the outer surface, because now this outer conductor is uncharged. So we could say that sigma on the outer surface times area of the outer surface will be sigma on the inner times the area on the inner. And of course, we need a, you know what I made? I made a mistake, because if this is positive, this had to be negative. So I really should have done Q of the line is negative Q of the inner surface. Put minus signs in here. So I apologize for that. Okay, because they have to be opposite sides. This has to be positive, this has to be negative to shield the electric field in here. And then since the outer conductor is neutral, we need to say something like this, that they're equal, the coulombs per meter squared times the meter squared, or the coulombs on the outside, is negative of the coulomb on the inside, and that makes the whole conductor neutral. So we can say sigma on the outside times 2 pi r, 2r L equals sigma on the inner surface times, okay? And so what we're left with, if we do the algebra, is positive, I lost a minus sign, 2 minus signs. The negative here, and then the negative here. Hopefully I'm not making so many mistakes that the notes are not followable, but there we are. All right, so I'll pause, give you a chance to copy this down. Okay, so are you ready for another more difficult example? Okay, well, here it is. I'm going to recycle this diagram. But what we're going to do is eliminate this conductor in the middle. Okay, so we just have a shell. Okay. So a shell that's a solid material, like maybe it's made of plastic or styrofoam, and so this inner radius right here is 3r, this is 4r, there's a hole in the middle, and all this styrofoam is a certain charge density, a certain coulombs per meter cubed, a certain concentration of charge spread through that styrofoam. And I want to find the electric field in all the regions. Okay, so the first region for r less than 3r. Well, what I have to do is I have to create a Gaussian surface inside this inner region. So what I'm going to do is just make a cylinder in here, like this, of a certain length L. It's just floating there, coaxial with this cylinder, in the empty space. So, Gauss's law for that surface and as it turns out, there's no charge in that Gaussian surface. So the Q enclosed is 0. And maybe we could put over epsilon 0 if you want, but it's still 0. And that means the electric field is 0. So, easy, right? I'll pause, give you a chance to jot that down. Okay, now, how about in here, in this region? In other words, greater than 3r, but less than 4r. So we need a Gaussian surface to use Gauss's law. With a cylindrical symmetry, we use a cylinder. So here is our cylinder. I'm going to make a cylinder like this. Actually, let me move it down a little bit. There it is, okay? It's got a certain length L. And we're going to start by applying Gauss's law to that cylinder. Again, remember that circle is important. It means a closed three-dimensional shape. So this is closed off, right? And EdA equals Q enclosed over epsilon 0. All right, left side of Gauss's law. Always just E comes out, you're integrating over the surface area of this cylinder, which opens up as a rectangle. 2 pi r L is the surface area. So let's go ahead and fill that in. Oh, I'm going to need a little bit more room. Okay, time to take a deep breath. The Q enclosed, okay? Basically, it's charge density times the volume of where the charge is over epsilon 0. So the charge density was given as plus rho. But what is the volume of where the charge is? So the volume of a cylinder, another formula you need for cylindrical symmetry is pi r squared, the surface area of a circle, times the length. It's area times length. So I'll write pi little r squared times L. So that's the area of this entire shape. But if we leave it there, mathematically we're saying that the charge extends all the way throughout the cylinder, but there's a hole here with no charge. So the cylinder, the charge only exists like right here, right? In that region. So maybe I could color coordinate here. And we have to subtract off this hole, which has an area, a volume of pi r L. And there is the Q enclosed over epsilon 0. Now all that's left is a little algebra to touch it up. So this becomes 9 pi r squared L, and then we could see the L's all go away. They're in every term. That happens with cylindrical symmetry. By the way, the length of the cylinder should always drop out. And then we have as our electric field E equals, and also notice the pi's go away. There's a pi in all terms. So we could say 1 over 2 epsilon 0. And then we have the rho times r squared divided by r gives us r to the 1 power. And then 9r squared divided by r and there is the electric field, okay, inside this region, okay, in this region here. We could do a unit check again. As I always recommend, we need the units of K coulombs per meter squared. Is that what we have? Well, we have 1 over epsilon 0 here. That gives us the units of coulombs constant. Rho has units of coulombs per meter cubed. And then we have some number of meters here. Minus meters squared over meters gives us some different number of meters here. But when you subtract meters minus meters, you end up with the unit of meters inside these parentheses. And you see we have K coulombs per meter squared. So seems like it has the right form. Okay? One more region to go. Oh, I need to pause and give you a chance to copy this down. Okay, so one more region to go. Outside here, so pretty soon I'm going to have to erase this, but before I do, in order to get the electric field out here, what I need to do is draw a Gaussian surface that now encloses the entire pipe, hollow pipe, certain length L like this. And so, well, maybe I'll just do it here. But I don't want to lose that formula. Well, I guess I'll have to because, you know what, maybe if, yeah, I guess I'll just have to. I don't want to erase the diagram just yet. All right, so this is a little awkward because of the limited board space. So for R greater than 3R, in other words, outside the pipe, apply Gauss's law. So there, we write out Gauss's law as always, and then the left side of Gauss's law just becomes E times area. Okay. The Q enclosed will be charge density times volume over epsilon 0. So we've got to do a similar sort of calculation that we had before. Charge density times the volume inside of where our charge is. So our charge now doesn't expand all the way out to the Gaussian cylinder. It's confined to this part of the pipe. So that's the volume we've got to multiply by, the volume of this pipe region without the hole in the middle. And so what we could say is it's pi r squared L. There's the volume of the entire pipe. We have to subtract off the volume of the hole because there's no charge there. So pi 3r squared L over epsilon 0. And now all we have to do is touch this up to get a final answer for E. So this is 16 r squared and 9r squared. 16 minus 9 gives us 7. So this becomes plus rho 7 pi r squared L over epsilon 0. Okay, the L's cancel, the pi's cancel. The constant 7 over epsilon 0 divided by 2 gives us 7 over 2 epsilon 0. The pi's went away, I said, and so what we have is rho r squared over little r. Okay, a unit check. So we need K coulombs per meter squared. Do we have that? Well, the 1 over epsilon 0 gives us the units of K. Rho is in coulombs per meter cubed. Do that a little bit bigger. Then we multiply by meters squared. And then we divide by another meter. So that gives us K coulombs over meters squared. So the formula appears to have the right form. So let me pause, give you a chance to write that down. Okay, so last thing we're going to do is graph. So the electric field is 0 inside the hole. In the region here, the formula that I had to erase, where did I have it? Well, I don't remember what it was. I thought I had it here. Ah, here we are. Okay. 1 over 2 epsilon 0 rho r minus 9r squared. So you have this in your notes, okay? So all these formulas, that's what we've got to plot. All right, so here is our electric field graph. 1r, 2r, 3r, 4r, and then 5, 6, so on and so forth. And that's the variable r. So from 0 to 3r, we have 0 electric field. Maybe I'll do it in a different color so it shows up better. From 3r to 4r, we've got to plot this formula. So again, the AP says for some reasonable curve. So you can do a concave up or a concave down function. It doesn't matter. It turns out it's concave down. Remember I said there's this little trick if you have time where you could just take the variable essence of a formula and take the derivative twice. So this is 1 minus negative 1 r to the minus 2, which makes plus. Take the derivative again, and we have negative 2 r to the minus 3. So you see you have a negative second derivative. It's a concave down function. Not necessary, just know that it's some kind of curve. And then from there, we have this formula, which has a 1 over r dependence, which will go like this. So we could say proportional to 1 over r, this just some other kind of function. And we could do we can add a transition value here by just plugging in 4r into this formula. 4r right here gives us 7 rho r over 8 epsilon 0. I believe I did that right. Hopefully I did that right. So there it is, the graph. Let me pause, give you a chance to write that down. Okay, so that was Gauss's law for cylinders. So the left side of Gauss's law for cylinder, first of all, the Gaussian surface you always pick for cylindrical symmetry is a cylinder. The left side of Gauss's law then becomes, I guess I erased it all, E times the surface area of this outer edge, which is the length of the cylinder times the circumference, 2 pi r, times L. And then the challenge is finding Q enclosed. We use lambda times length, coulombs per meter times meter, or we use rho times volume. And then, of course, the volume of a cylinder is pi r squared L. Sometimes we had to do that minus the hole where there was no charge. So we had pi r squared L minus pi r squared L, and we got the Q enclosed over epsilon 0. So I'll see you in the next physics video.